So imagine you are just driving an electric vehicle down the highway.
Okay, I'm picturing it.
Yeah, you are cruising at like 70 miles per hour, maybe listening to some music. You're totally relaxed.
Just normal commute.
Exactly. The hum of the tires, the wind slipping over the hood. But right beneath your feet, separated by just a few millimeters of aluminum and steel, sits this massive, incredibly dense, high-voltage battery pack.
Right, which is basically a localized power plant.
Literally.
Yeah.
We are talking about an 80 or maybe a 100 kilowatt-hour energy reserve. It is just this powerhouse of electrochemistry waiting to be unleashed.
And unleashing it is what makes the car move, obviously.
Like when you press the accelerator, hundreds of amps of current just surge out of those cells. And then when you brake, that energy gets violently shoved right back in.
It's a lot of energy moving very quickly.
So what is the single most critical factor keeping that massive battery pack safe from, a catastrophic thermal runaway?
Well, most people would probably think it's the heavy ballistic armor on the bottom.
Right, or maybe the liquid cooling system, right? The thing pumping gallons of chilled glycol through the pack.
Yeah, those are definitely important, for sure. But the absolute most crucial line of defense isn't a shield or a radiator.
No.
No, it is actually the vehicle's sense of touch.
It's sense of touch. I like that phrasing.
Yeah, that concept of awareness is basically the entire foundation of modern automotive safety.
How so?
Because if the battery management system, like the digital brain orchestrating all that energy, if it cannot accurately feel how hot or cold those individual cells are, every other safety mechanism is flying completely blind.
Oh, wow. So if it goes numb, everything else is useless.
Exactly. The cooling pumps don't know when to turn on.
Yeah.
The charging algorithms don't know when to throttle back.
The car is just guessing at that point.
Right. If the car goes numb to temperature, the entire system is operating on assumptions instead of actual data.
And assuming a battery is cool when it is actually boiling.
That is exactly how you lose a vehicle. It's incredibly dangerous.
Numb. I mean, that is just a terrifying word when you were talking about 80 kilowatt hours of stored energy.
It really is.
And that is exactly what we are exploring today.
Yeah.
We are acting as digital detectives for this deep dive.
We have some really fascinating source material for this one.
We do. We are diving into a highly specialized piece of internal engineering documentation. It's the technical specification detailing the 5 dimensions of safety for high-voltage batteries.
And we are going to focus our lens entirely on the second dimension today, right?
Yes, exactly. The physical sensor and front-end acquisition layer. We are going to decode 3 specific, highly critical error codes that basically keep battery engineers awake at night.
Those would be P0A9C, P0A9D, and P0A9E.
Right. And if you plug a standard OBD2 scanner into a modern EV, those codes might just look like, random alphanumeric soup.
Just gibberish to the average driver.
Exactly.
Mm-hmm.
But they actually tell a massive story of physical trauma, electrical deception, and the incredible lengths engineers go to just to keep that sense of touch intact.
Because the documentation we are analyzing, it is dense. It is full of fail-safe logic, manufacturing tolerances, testing protocols.
A lot of math and jargon.
It really is. But beneath all that, it is fundamentally a story of anticipating chaos.
Anticipating chaos. Because the physical world is messy.
Exactly. Automotive engineers have to assume that the physical world is actively trying to destroy their hardware.
Right, because it basically is.
They're designing a system that has to survive a decade of potholes, blizzards, desert heat waves, constant high-frequency vibration.
All while being submerged in a sealed box carrying hundreds of volts.
Yeah, so the goal isn't just to make a sensor that works in a pristine lab.
It has to survive reality.
More than that, it is about designing an intelligence network smart enough to recognize when its own sensors are being destroyed. Or even worse, when they are actively lying to the computer.
Which is such a crazy concept to me, a lying sensor. So if you have ever wondered just how much paranoid, fail-safe engineering goes into the car sitting in your driveway, this is the ultimate behind-the-scenes story.
It really is a fascinating journey.
Let's unpack this from the ground up. Before we can talk about the software algorithms that fix a problem, we really need to understand the physical reality of what is breaking.
We have to look at the physics at the crime scene, basically.
Right. And to do that, we have to introduce the unsung hero of our story.
The NTC thermistor.
Yes, the negative temperature coefficient thermistor. It is this tiny, unassuming ceramic bead.
It's usually no bigger than a grain of rice, honestly.
But it carries the weight of the entire thermal safety strategy for the whole vehicle.
It does. And to understand how it fails, we first have to understand how it actually succeeds.
So let's talk physics.
The core physics here rely on a very specific relationship between temperature and electrical resistance.
Okay, break that down for me.
Well, these thermistors are made from semiconductor materials, usually metal oxides like manganese, nickel, or cobalt.
Okay, semiconductors.
Right. And because they possess a negative temperature coefficient, their behavior is the exact inverse of a standard metal.
So it acts backwards.
Exactly. With a regular copper wire, as it gets hotter, electrical resistance increases. The heat makes it harder for electrons to flow.
But the NTC is negative, so it does the opposite.
Yes. As the ambient temperature goes up, the thermal energy excites the electrons in the semiconductor. They jump the band gap, they become free charge carriers, and as a result, the electrical resistance of the component goes down drastically.
I love visualizing invisible physics like this. So, let's try an analogy here.
I am all for a good analogy.
Let's think of the NTC thermistor, like a really stubborn bouncer at a very exclusive nightclub.
Okay, a bouncer. I like it.
The nightclub itself is the electrical circuit. And the crowd of people outside trying to get in, that is the electrical current, the electrons.
Makes sense.
So when it's cold outside, when the temperature of the battery cell is low, this bouncer scans incredibly firm.
He is rigid.
Right, he has high resistance, he crosses his arms, he blocks the door, and he lets almost no one through. The current is barely trickling in.
That paints a very clear picture, actually. High resistance translates to incredibly low current flow.
Because the bouncer's doing his job.
Right, and the system measures that tiny trickle and knows, okay, the environment is cold.
But as the battery cell starts working hard, as things heat up inside the pack.
The bouncer starts to feel the heat.
Exactly. He starts sweating, he gets tired, he loosens up, his resistance drops significantly.
And because his resistance drops, he steps aside.
Yes, and he starts letting the crowd, the current, flow freely into the club.
So the hotter the room gets, the less resistance he offers.
And the more current pours through the door.
Which is brilliant because by measuring exactly how many people the bouncer is letting through at any given microsecond, the car's computer can perfectly calculate the ambient temperature of that exact spot.
It just watches the flow of electrons.
Right. And that measurement is happening continuously, thousands of times a second.
Wow, thousands of times.
Yeah. The battery management system, the BMS, monitors that resistance curve constantly. It dictates the electrochemical reaction rates based on that curve.
It uses it to set limits, right?
Exactly. It calculates the maximum available discharge power, the allowable charging speed, basically the fundamental thermal safety of the entire pack.
Because the engineering spec we are looking at explicitly calls temperature the first indicator of intrinsic safety.
It is the canary in the coal mine for thermal runaway.
But, like any physical component living in a hostile environment, this tiny thermistor is vulnerable.
Oh, highly vulnerable. Both the thermistor itself and the delicate low-voltage wires connecting it to the computer.
Which brings us to the first of our three major failure modes, the error code P0A9D.
Ah, yes, P0A9D.
The documentation defines this as a circuit low voltage, which is fundamentally caused by a short circuit.
A dead short.
And reading through the mechanical causes of this, it honestly just sounds like sheer brutality.
The inside of a battery pack is not a gentle place.
Right. We tend to think of electronics as these pristine things, sitting quietly in static server racks.
But inside a high-voltage battery pack, it is essentially an industrial construction zone.
Yeah, you have these incredibly heavy battery modules. Sometimes they weigh 100 pounds each.
And they are packed shoulder to shoulder into this rigid metal casing.
And running right over the top of these modules are heavy, solid copper bus bars.
Right. And these aren't flexible little wires. They are thick, rigid bars of solid metal.
Carrying massive traction currents. The kind of current needed to launch a 2-ton vehicle from 0 to 60 in 3 seconds.
So that architecture creates a highly perilous environment for any delicate low-voltage signal wires.
Because they have to weave through all that heavy metal infrastructure.
Exactly. The delicate wire harnesses connecting our tiny NTC thermistors back to the BMS have to navigate a maze of heavy, sharp metal.
The documentation actually points out that during the initial stacking of these modules at the factory, there is extremely limited physical clearance.
Sometimes just fractions of a millimeter.
Right. So if the routing of a delicate sensor wire is off by even a tiny bit, it can get pinched.
These wires can easily be sliced by the sharp, stamped metal edges of the battery frame.
Or literally crushed under the sheer weight of the cover plate being bolted down by a robot.
But even if a wire survives the factory floor flawlessly, it still has to survive the real world.
The roads are brutal.
Once the car is out there, hitting potholes, crossing train tracks, just vibrating constantly for years.
Those heavy, high-voltage copper bus bars sitting right above the signal wires can continuously press and rub against them.
Over thousands of miles, that harmonic vibration acts literally like sandpaper.
It just slowly, mechanically scrapes away the protective plastic insulation surrounding the delicate sensor wire.
And the physical erosion of that insulation is the primary catalyst for P0A9D.
Because once the plastic is gone, the raw copper signal wire is completely exposed.
And electricity, by its very nature, is incredibly lazy.
It always takes the easiest path.
Right, the path of absolute least resistance. So if that exposed signal wire rubs against a neighboring exposed wire, or if it touches the metal chassis of the vehicle.
Which is tied to the electrical ground.
Exactly. The moment it touches ground, you have created a hard short circuit.
Let's bring that back to our bouncer analogy for a second, or rather, the electrical reality of what the computer sees when that short circuit happens.
Okay, let's do it.
If the current suddenly finds a shortcut to the ground, before it even reaches the bouncer at the club door, what happens to our resistance measurement?
Well, the resistance effectively ceases to exist in the eyes of the computer.
It just vanishes.
The short circuit creates a bypass that completely routes around the thermistor. So, electrically speaking, the resistance drops to virtually 0 ohms.
0 ohms. And because the system relies on a specific circuit topology to read the sensor, which we will dissect shortly, when the resistance drops to 0, the analog voltage that the computer is monitoring is violently dragged down.
It drops to almost 0 volts. The signal completely bottoms out.
The system suddenly sees, like, 0.05 volts.
And it instantly recognizes that the physical pathway has collapsed. It throws the P0A9D code immediately.
So a crushed or rubbed wire drops the voltage to 0. But the engineering spec details the exact opposite problem as well.
Right, failure mode number 2.
P0A9E. This is defined as a circuit high voltage, which indicates an open circuit.
A broken path, basically.
And the underlying mechanism for this one is fascinating because it doesn't require a heavy copper bar crushing a wire.
No, this one is much more subtle.
It is an invisible force.
Yeah.
It's basically a microscopic war happening inside the sensor itself.
The document refers to it as the coefficient of thermal expansion mismatch. The CTE mismatch.
CTE mismatch, that sounds intense.
It is. To really grasp how destructive this is, we have to look closely at the anatomy of the NTC probe itself.
Okay, zooming in.
We have this sensitive ceramic semiconductor chip, right? That's the brain of the sensor.
The actual bead.
Right. And to protect it from the harsh environment, engineers completely encase it in a hard shell of protective epoxy resin.
So it's a sealed, unified little bead.
But the ceramic chip and the epoxy shell are fundamentally different materials. They are completely different molecular structures.
Which means they react to thermal energy differently.
Precisely. All materials expand when heated and contract when cooled, but they do so at wildly different rates.
Their coefficient of thermal expansion.
Exactly. Ceramic generally has a very low CTE. It doesn't want to expand much at all when it gets hot.
It likes to stay the same size.
But epoxy resin, being a polymer, has a much higher CTE. It wants to swell significantly when it gets hot.
So you have two materials, permanently bonded together, experiencing the exact same temperature swings inside the battery. But one is trying to expand far more than the other.
Yes.
I am picturing two people chained together by the ankle, trying to walk at completely different speeds.
That is a perfect visualization.
Eventually, something just has to snap.
That is exactly the internal stress happening here. Every time you drive the car, the battery heats up, the epoxy tries to swell, pulling aggressively on the ceramic.
And pulling on the microscopic internal bonding wires, too.
Yes. And then every time you park the car in the cold, the epoxy violently contracts, crushing inward.
So over thousands of driving cycles, experiencing severe thermal shock from, freezing winters and blistering summers.
This microscopic tug-of-war causes the epoxy encapsulation to develop microcracks.
That sounds bad.
It is, but far more catastrophically, the internal gold or copper bonding wires, the tiny physical connections smaller than a human hair that link the ceramic chip to the external wire, they suffer from extreme physical fatigue.
Like bending a paper clip back and forth until it breaks.
Exactly. The constant stretching and compressing eventually cause the metal lattice to yield, The wire simply snaps inside the resin.
Wow. An invisible snapping of a microscopic wire inside a sealed bead. The sensor looks perfectly fine from the outside, but internally it's totally dead.
And the spec also mentions that this open circuit can happen externally, too, through sheer vibration.
Oh, really? Just shaking it apart?
High-frequency chassis vibration traveling up through the suspension can cause the metal connector pins on the wiring harness to slowly wiggle loose.
Ah, I've heard of that. Fretting corrosion.
Yes. Fretting corrosion and pin pullout, where the connector physically backs itself out until it unplugs entirely.
Whether it is an internal microwire snapping from CTE fatigue or a connector pin vibrating loose from the socket, the electrical result is identical, right?
Yes. It is an open circuit. The physical pathway for the electrons is completely severed. The bridge is out.
So in an open circuit, going back to our nightclub, the bouncer hasn't just crossed his arms. The entire door to the club has been bricked over.
No electrons can cross the gap whatsoever.
And because that pathway to ground is severed, the voltage read by the computer behaves completely differently than in a short circuit.
It's the exact opposite, yeah.
Instead of being dragged to zero, the voltage shoots upward. It is forcefully pulled up by an internal resistor on the circuit board to the maximum reference voltage of the system.
Which is typically a flat 5.0 volts.
Right, so the system reads 5 volts and immediately knows the connection has been lost.
And it triggers P0A9E.
Okay, so a crushed wire drops the signal to 0, and a snapped wire shoots the signal to 5.
The computer can clearly and definitively see both of these extremes.
They are undeniably broken. There's no ambiguity at all.
None. But that brings us to the third failure mode, P0A9C.
Ah, this one. The document defines this as a rationality, range, or performance anomaly.
In common engineering parlance, it is a sensor drift.
And this is by far the most insidious failure the system has to combat.
It is incredibly tricky to handle.
It is insidious because a drifting sensor isn't broken enough to trigger those absolute 0 or 5-volt alarms.
Exactly. With P0A9C, the sensor is still transmitting a signal, and that signal falls squarely within the theoretically normal operating voltage of the system.
So the computer looks at the raw data and says, okay, 2.5 volts, that translates to a perfectly reasonable temperature.
The problem is the sensor is lying.
Right. The dynamic characteristics it is outputting completely contradict the actual physical thermodynamic reality of the battery pack.
It is effectively gaslighting the battery management system.
Which is wild. How does that happen? How does a physical sensor learn to lie?
Well, the engineering documentation highlights two primary environmental mechanisms that cause this deception.
Okay, what's the first one?
The first involves water intrusion. It creates what is known as a parasitic parallel leak.
Parasitic parallel leak. Okay, let's consider the operating environment. A battery pack is a sealed aluminum enclosure, but, seals degrade over time.
Or, even if the seal is perfect, you might be operating in a high-temperature, high-humidity environment.
Like driving in Florida in the summer.
Right. As the pack heats and cools, the internal air pressure fluctuates. This naturally draws in humid air through the Gore-Tex pressure equalization breathing valves.
The pack has to breathe.
It does. But when the pack cools down at night, all that humidity inside condenses.
You literally reach the dew point.
And the inside of the battery pack begins to sweat.
Water and high-voltage electronics.
Right.
That is a combination that immediately makes me nervous.
As it definitely should. If that condensation seeps into the NTC probe itself, maybe through one of those CTE microcracks we just discussed.
Oh, right, the microscopic cracks in the epoxy.
Exactly. Or if it settles across the surface of the printed circuit board where the sensor's pins are soldered, water acts as a conductor.
It's not a great conductor, but it conducts.
It is a poor conductor compared to copper, but it is conductive enough. It creates a microscopic, unintended pathway for electricity to flow across the circuit board, completely bypassing the NTC thermistor.
Ah, so that is the parasitic parallel leak.
Yes, it usually has a very high impedance, often in the mega-ohm range, so it doesn't allow enough current through to cause a massive 0-volt short circuit.
It's not a dead short.
No, but it slightly, persistently lowers the overall measured resistance of that specific circuit channel.
Going back to our nightclub analogy, it is as if someone secretly opened a tiny bathroom window at the back of the club.
I love that, yes.
A few people are quietly sneaking in through the window, bypassing the bouncer completely.
The bouncer has absolutely no idea.
So the club management, the computer, miscalculates how crowded the room actually is.
That translates perfectly to the electrical math because the system sees a slightly lower total resistance.
And lower resistance equals higher temperature.
The computer is mathematically forced to artificially inflate the temperature reading.
Wow.
The actual physical temperature of the battery cell might be a perfectly safe, comfortable 25 degrees Celsius.
But the moisture-induced parallel leak lowers the resistance just enough that the sensor reports a fake, nonlinear spike to like 45 or 50 degrees Celsius. So the car's brain thinks the battery's overheating when it's actually perfectly fine.
Exactly. It's a false positive.
That is annoying, for sure. I mean, it might limit your power or turn on loud cooling fans unnecessarily.
Yeah.
But the second cause for this drift failure mode, the physical detachment, that one is downright terrifying.
Because it does the exact opposite.
Right. It hides a real thermal event.
Physical detachment is basically a worst-case scenario for sensor drift.
How does it physically happen?
Well, in many pack architectures, these temperature sensors are mounted by gluing them directly onto the bare aluminum casing of the battery cells.
Using specialized thermal glue.
Right, a high-temperature thermal structural adhesive. But adhesives are just polymers, and over time, they degrade.
They dry out.
If that adhesive ages, dries out, or if those shear forces from thermal expansion literally tear the glue bond apart, the tiny sensor can physically pop off the side of the battery cell.
It just detaches completely.
Yeah.
So it is no longer making physical contact with the metal casing of the cell it is supposed to be monitoring.
It is just hanging there.
Suspended by its own wire harness, dangling in the empty air gap between the battery modules.
It is literally measuring the ambient breeze inside the battery box.
Meanwhile, the chemical cell right next to it, the one it is supposed to be pressing against, could be failing.
It could be shorting internally, rapidly heating up, melting down.
And approaching the critical threshold of thermal runaway.
And that creates a massive, localized blind spot.
Because air doesn't transfer heat well.
Exactly. The physics of heat transfer explain why this is so dangerous. Air is an abysmal conductor of heat compared to aluminum or copper. It is essentially an insulator.
So the suspended sensor is insulated by the boundary layer of air surrounding it.
It will read an ambient temperature that is significantly lower than the actual internal chemical core temperature of the battery cell right next to it.
The cell could be hitting 80 or 90 degrees Celsius, a critical danger zone.
And the detached sensor is happily reporting to the BMS that the local environment is a cool, comfortable 30 degrees.
This presents such a fascinating, almost philosophical engineering problem.
It really does.
You have a brain, the battery management system, that relies entirely on a nervous system made of these delicate sensors.
But those sensors can be crushed by heavy metal.
Right. They can snap from their own internal thermal stress.
They can be short-circuited by morning dew.
Or they can literally fall off and lie to the brain about a fire.
Exactly.
So, since the physical world is this chaotic, and we have to accept the reality that sensors will eventually fail or drift, how does the digital brain figure out what is real and what is a glitch?
How do you design a computer that knows when to stop trusting its own nervous system?
Exactly.
Well, that is the transition from mechanical vulnerability to digital resilience. It brings us to the second major dimension of the engineering specification we're looking at.
The technical architecture and the fail-safe diagnostics.
Right. It is all about how the BMS acts as a hypervigilant digital detective.
I love that framing, the digital detective.
And the investigation starts at the very foundation of the hardware logic. We need to look at how the physical resistance is translated into a digital language the computer can actually understand.
Because a microprocessor doesn't inherently understand resistance.
No, it only understands ones and zeros. Digital logic.
The spec details a very specific circuit topology to bridge this gap.
It says the BMS uses a precise 10K ohm pull-up resistor.
Okay, a 10K ohm pull-up resistor. This resistor is paired with our NTC thermistor to create a voltage divider circuit.
Yes.
The resulting analog voltage is then fed into an analog to digital converter, an ADC chip.
And from there, the computer uses a complex mathematical formula called the B-parameter equation.
Which is a simplified version of the Steinhardt equation, right?
Exactly. It uses that to translate the raw digital number into an actual temperature reading in Celsius.
Before we get to the math, let's break down that hardware. What exactly is a voltage divider, and why are we using a pull-up resistor instead of a pull-down?
Well, a microprocessor's ADC, the analog to digital converter, can only read voltage. It literally cannot read resistance directly.
So we have to convert a changing resistance into a changing voltage.
Right. A voltage divider is a simple circuit that does exactly what it sounds like. It takes a reference voltage in automotive applications, almost universally a highly stable 5.0 volts.
Okay, 5 volts.
And it divides it across two resistors in series. The first resistor is a fixed known value inside the BMS. In this spec, it is a highly precise 10,000 ohm or 10K ohm resistor.
And the second resistor in the series is our NT thyristor out in the battery pack, whose resistance is constantly changing with temperature.
Exactly.
So as the thermistor's resistance changes, the ratio between the two resistors changes.
Which means the voltage measured exactly between them fluctuates.
It is like a seesaw of electrical pressure.
That's a good way to put it.
But why a pull-up resistor? Why is the fixed 10K resistor tied to the 5-volt line, pulling the signal up, rather than tied to the ground line?
It comes down to fail-safe engineering and identifying the most likely failure modes.
Okay, what's the most likely failure?
In a vehicle, the most common wiring fault by far is a short to ground, where a wire rubs against the metal chassis.
Like we talked about earlier with the bus bars crushing the wires.
Right. If we used a pull-down topology, a normal, very hot battery reading might look like 0.5 volts. But a dead short to the chassis also looks like 0 volts.
Oh, I see. They ate too close together.
It becomes mathematically very difficult to quickly distinguish between a battery that is operating at its maximum thermal limit and a broken wire.
The computer might confuse a short circuit for a really hot battery.
Exactly. By using a pull-up topology, a short to ground violently yanks the signal away from the normal operating range, down to near 0.
Making it instantly recognizable as a critical fault.
You engineer the circuit so that failures look as dramatically different from normal operation as physically possible.
That makes perfect sense.
Ah.
So the ADC reads this fluctuating voltage. Let's say it sees 2.5 volts. Now the software has to translate that into Celsius.
And it uses the Steinhart equation, or the B-parameter equation.
This isn't just a simple multiplier, right? It's not like saying 1 volt equals 10 degrees, 2 volts equals 20 degrees.
Far from it. The behavior of semiconductor materials like our NTC is highly nonlinear.
It's a curve.
The resistance drops on a logarithmic curve. The Steinhart equation is essentially a complex mathematical Rosetta Stone.
Rosetta Stone, I like that.
It uses natural logarithms and specific material constants, the B parameter, to map that nonlinear voltage curve perfectly to a linear temperature scale.
It is heavy, processor-intensive math.
And it is running continuously for perhaps over 100 different sensors simultaneously.
And this mathematical translation is exactly where the engineers have to impose strict, unbreakable boundaries.
The hard limits.
Right. The spec dictates hardware limits. It says if the analog to digital converter sees a voltage less than 0.2 volts, the software is explicitly forbidden from running the B-parameter equation.
It doesn't even attempt the math.
It instantly throws a red flag, declares a P0A9D hard short circuit, and refuses to believe whatever temperature that low voltage translates to.
Yeah.
Conversely, if it sees a voltage greater than 4.8 volts, it instantly declares a P0A9E open circuit.
Also refusing to run the math.
So why do we need these hard limits? I mean, if the math formula is so accurate, why not just let it calculate the temperature no matter what raw voltage comes in?
Because if you allow that logarithmic math to process a broken signal, the consequences are disastrous.
Oh, so...
The computer has no common sense, right? It only knows the math.
True.
Consider the B-parameter equation applied to a short circuit. If a wire gets crushed against the chassis and the voltage drops to 0.05 volts,
The equation doesn't know the wire's broken.
it just plots 0.05 volts on its logarithmic curve. Mathematically, it might translate that near zero voltage to a temperature of 150 degrees Celsius.
Which is beyond a boiling. That is an incredibly hot battery cell.
It is far beyond the threshold of catastrophic thermal runaway.
It's on fire.
Exactly. If the system was allowed to believe that calculation, it would conclude that the vehicle is literally on fire.
And what would it do?
Its programmed response to a 150-degree cell would be to violently and immediately command the high-voltage contactors to open, severing all power to the wheels.
Oh, wow. Imagine cruising at 70 miles per hour, and your car instantly kills all power, throws up a critical failure warning, and perhaps even triggers an active fire suppression system.
All because a tiny wire rubbed against a piece of aluminum.
A phantom fire.
Exactly.
Oh.
The 0.2-volt floor prevents the car from panicking over a fire that doesn't exist.
Okay, what about the upper limit, the 4.8-volt ceiling? If a wire snaps internally from CTE fatigue and the pull-up resistor yanks the signal to 5 volts, what happens if the math is allowed to run on that?
Again, the math follows the curve. A 5-volt signal represents near infinite resistance.
Right.
Mathematically, the B-parameter equation will calculate that infinite resistance as an impossibly cold environment.
How cold?
It might register the temperature as negative 40 degrees Celsius.
Extreme deep freeze conditions.
Exactly, and the battery management system has a programmed response for extreme cold too.
Because lithium-ion batteries hate the cold.
Right. They cannot be charged safely below freezing.
Yeah.
It causes lithium plating, which permanently destroys the cell.
So if the system believes the battery is at negative 40 degrees, what's its priority?
Its immediate priority is to warm the pack up. It will activate the internal PTC positive temperature coefficient high voltage coolant heaters.
It turns on the heater.
It commands them to blast maximum heat into the fluids circulating through the battery.
Wait, but the battery isn't actually cold. It might be a warm summer day. The pack might already be sitting at 35 degrees Celsius.
Precisely the danger. The battery is warm, but the snapped wire makes the computer think it's freezing.
So you have a perfectly warm, healthy battery being blasted with maximum thermal energy by its own internal heating system.
If this is allowed to continue, the car will accidentally cook its own battery pack.
It would push a healthy cell into a very real thermal runaway.
The vehicle would essentially set itself on fire, trying to prevent a phantom blizzard.
That is profound. The car's own automated safety mechanisms become the weapon of its destruction if the data is corrupted.
Which is exactly why those hard voltage limits, less than 0.2, greater than 4.8, are the absolute bedrock of the digital detectives protocol.
They establish the perimeter of reality.
They prevent the car from reacting to phantom fires and phantom blizzards.
But, as we discussed earlier, those limits only catch the definitive, catastrophic breaks. They only catch the crushed wires and the snapped pins.
The obvious failures.
Right. What about the liars? What about the P0A9C drift failures, where a moisture leak or a detached sensor results in a voltage sitting right in the middle of the normal range? Let's say 2.5 volts.
The voltage is mathematically valid, but physically completely fake.
Exactly. How does the detective catch a lie?
Catching a drift failure requires moving beyond simple voltage thresholds. You have to utilize both time and space to cross-examine the data.
Time and space. Okay, let's examine the temporal check first.
The software logic has to interrogate the behavior of the temperature reading, not just the absolute value.
The documentation mentions a metric called DTDT.
Yes, the BMS software continuously calculates and monitors DTDT. That is the delta of temperature over the delta of time, or simply the rate of change.
The rate of change. The engineering spec highlights this as a primary diagnostic tool, and it relies on a fundamental, inescapable law of thermodynamics, thermal mass.
Right.
I like to think about thermal mass like trying to boil an Olympic-sized swimming pool.
That's a great visual.
You can take an incredibly powerful industrial heater and drop it straight into the pool, but the water temperature is not going to instantly jump 50 degrees in 1 second.
It is physically impossible.
Because water possesses an enormous thermal mass. It takes a massive amount of energy and a significant amount of time to raise the temperature of that much matter.
And that thermal mass is the software's biggest advantage here. A high-voltage battery pack is essentially a massive block of dense metals, copper, aluminum, nickel, cobalt, lithium interspersed with gallons of liquid coolant.
The whole assembly can weigh over 1,000 pounds.
The physical laws of thermodynamics dictate that the internal temperature of that much mass simply cannot spike instantaneously.
Even if a cell is on fire.
Even if a cell is dead shorted internally and dumping all its energy into heat, the temperature curve will still have a specific measurable upward slope.
It takes time to heat up metal.
So the software acts like a lie detector watching a heart rate monitor. It constantly watches the slope of the temperature curve reported by every single sensor.
So if the software calculates the DTDT and sees that a sensor is reporting a temperature jump of, say, 30 degrees Celsius in a single second,
the digital detective knows instantly that this reading violates the laws of physics.
it recognizes that a 1,000-pound battery pack cannot heat up that fast.
Therefore, the reading must be the result of a sudden drop in electrical resistance caused by a moisture short or an electrical glitch.
Not a real thermodynamic event.
Exactly. It flags the DTCD anomaly, catches the lie, and triggers the P0A9C drift code.
It catches the lie by deeply understanding the laws of physics, that is the temporal check, looking at the behavior over time. But the spec also details a spatial check, which sounds like something out of a geometry textbook.
The spatial adjacent matrix cross-check.
That is a mouthful.
The terminology is dense, but the concept is remarkably intuitive.
How does it work?
The BMS maps the physical location of every single temperature sensor in its memory. It knows exactly which sensors live next to each other on the same cooling plate or within the same module.
Okay, so it has a map of the neighborhood.
Exactly. Because the aluminum casing of the modules and the liquid cooling channels are highly thermally conductive, heat tends to spread out relatively evenly across a local area.
Translation. If one spot is hot, the spots right next to it should at least be warm.
Precisely. The system looks at its immediate neighbors to see if anyone is the odd one out.
So it runs a comparison.
The software constantly runs a comparative matrix. If you have a row of 5 sensors monitoring a module and sensors 1, 2, 4, and 5 are all reporting a stable 30 degrees Celsius.
But sensor number 3 is suddenly reporting 15 degrees Celsius.
The spatial cross-check throws an error. It knows that, realistically, one single spot on a thermally conductive aluminum plate cannot be drastically, inexplicably colder than the spots literally an inch away on either side.
It identifies the outlier. And that specific scenario reading, unusually cold compared to its neighbors, that is exactly what would happen if a sensor suffered from physical detachment, right?
Exactly.
If the glue failed and it popped off, it would be measuring the ambient air, dropping its temperature reading significantly compared to the sensors still glued to the hot cells.
The spatial matrix catches the detached sensor because its data no longer correlates with the physical reality of its immediate neighborhood.
Okay, so the digital detective is incredibly robust. It uses hard voltage asymptotes to catch the shorts and opens.
And it uses temporal thermodynamics and spatial geometry to catch the lying, drifting sensors.
But identification is only half the battle. What happens next? Once the system realizes a sensor is dead, crushed, or lying, what does it actually do about it?
Right, because it is a piece of software. It can't physically reach out and solder a broken wire back together while you are driving down the interstate.
The physical damage is permanent until a technician replaces the harness.
So the software has to dynamically reconfigure itself to keep the vehicle safe.
It goes into survival mode.
It enacts a complex limp home mode, a fail-safe state. And the primary mechanism for this survival mode is something the documentation calls the maximum temperature substitution strategy.
Maximum temperature substitution strategy. How does that work?
It is a brilliant piece of compensatory logic. If a single NTC sensor is confirmed to be dead or drifting, the software safety layer instantly filters out that broken channel.
It just ignores it completely.
It quarantines the data. But the thermal management system still needs a temperature value for that physical zone to run the cooling pumps and calculate the pack's power limits.
It needs a number to plug into the equations.
Right. So it dynamically looks at the temperature readings of the surviving healthy NTC sensors adjacent to the broken one.
The neighbors.
And it deliberately, automatically chooses the absolute highest temperature reading among those neighbors to use as a substitute value for the blind spot.
Wait, I have to push back on the logic there.
Okay, why?
Why default to the highest? If I lose a sensor and I want to guess the temperature of that missing spot, wouldn't it be far more statistically accurate to take an average of the surrounding sensors?
That seems logical, yes.
Like if the left reads 30 and the right reads 34, guessing 32 seems like the most logical, accurate approach. Why purposefully choose the hottest one?
Because accuracy is secondary to safety.
Oh.
That question cuts to the absolute core philosophy of high-voltage battery engineering. In this field, you never, ever assume the best-case scenario. You don't even allow yourself to assume the statistically average-case scenario.
You must mathematically enforce the worst-case scenario.
Paranoia as a design principle.
Wow.
Consider the physical reality. That blind spot might actually be the hottest part of the module.
That's true.
Perhaps the cell in that exact location has a slightly higher internal resistance and is working harder than its neighbors, generating more heat. If you take an average of the surrounding sensors, you are artificially dragging down the assumed temperature of that blind spot.
See the danger.
If you assume the average, the BMS thinks the zone is cooler than it actually is.
It might not spin the cooling pumps fast enough.
It might allow the driver to pull too much power.
By substituting the absolute highest surrounding temperature, you are forcing the system to overreact.
You are guaranteeing that the thermal management system will respond aggressively. It is infinitely better to overcool a battery pack than to undercool it.
You might sacrifice a tiny bit of aerodynamic efficiency, by running the radiator fans louder than necessary.
But you guarantee thermal stability.
That is a fascinating insight. You program the brain to be pessimistic because optimism leads to fires.
Exactly. So it substitutes the highest temp to stay on the safe side.
But the BMS doesn't just change a number in a spreadsheet. What does the system do physically to the car's operation to respond to this failure?
The BMS immediately broadcasts a critical torque reduction request over the vehicle's CAN bus to the VCU, the Vehicle Control Unit.
We talk to each other.
Together, they execute a strict derating strategy to minimize risk. First, they force the liquid cooling water pumps and the front radiator fans to 100% maximum RPM.
They just blast it.
They flood the entire pack with maximal heat dissipation capacity immediately, just in case that blind spot is actually getting hot.
You will definitely hear that as a driver. The fans will sound like a jet engine spinning up.
You will hear it and you will feel the next step. The VCU drastically limits the maximum electrical power the vehicle is allowed to discharge or charge.
So if you press the accelerator pedal to the floor, the car will feel incredibly sluggish.
It limits the current draw to prevent the blind cell from generating excess joule heating. And crucially, the software permanently bans DC fast charging.
Okay, DC fast charging. We are talking about pulling up to one of those massive 250 or 350 kilowatt roadside chargers that blasts energy into the battery to get you from 10 to 80% in 20 minutes.
Yes, those.
Locking that out entirely seems like a massive inconvenience for a driver who might just have a tiny rubbed wire. Why is that specific lockout so critical?
Because pushing 250 kilowatts of raw direct current into a battery pack is the most thermally stressful event the cells will ever experience outside of a track day.
It generates an immense amount of internal heat incredibly rapidly.
Pushing a battery at those speeds requires absolute microsecond precision in thermal monitoring. The BMS constantly adjusts the charging curve based on the temperature of the hottest cell.
So if you have a blind spot,
If you have a dead sensor, you simply cannot risk pushing that blind cell to the brink.
you're just guessing.
Right. If you fast charge without perfect thermal visibility, you could easily push that specific cell into thermal runaway without the computer ever seeing the temperature rise.
By the time the adjacent sensors feel the heat, the cell is already in chemical collapse.
Exactly.
So the system is essentially shutting down every risky behavior. No fast charging, limited acceleration, maximum cooling.
It treats a broken wire with the same severity as a failing battery.
And the engineering spec mentions one final, ultimate response. What if it's not just one isolated sensor that gets crushed?
A larger failure.
What if a major structural event severs an entire wiring harness and multiple sensors across different modules fail simultaneously?
If the system experiences a multi-node failure, what the engineers classify as system-level thermal blindness, it abandons the limp home strategy entirely.
Limp home isn't enough anymore.
No. The BMS concludes that it can no longer guarantee the safety of the vehicle under any operating conditions. It immediately triggers the highest level safety alert.
It flashes critical warnings on the dashboard, sounds audible alarms.
And instructs the driver to pull over safely immediately. And then it executes a high-level safety shutdown, physically opening the high-voltage main relay contactors.
It severs the connection between the battery and the rest of the car, isolating the energy completely.
It pulls the plug on the whole operation.
It chooses to strand the driver rather than risk a fire.
Absolutely.
Okay, so we've established how vulnerable the physical sensors are, and we've explored the incredibly complex digital acrobatics the computer performs to manage those failures after the fact.
But dealing with a failure is one thing, preventing it is another.
Right. Let's wind the clock back to the drawing board. This brings us to the third major dimension of our deep dive, designing out the flaws.
This is the DFMEA phase.
Design failure mode and effects analysis. How do engineers design the physical architecture of the battery pack so these failures are incredibly rare in the first place?
The DFMEA is a structured, highly analytical process where engineers sit in a room and brainstorm every conceivable way a component could fail.
And then they assign a numerical score to the severity of that failure.
Right. Exactly. Because a single temperature sensor failure can theoretically lead to undetected thermal runaway, which means a catastrophic vehicle fire. This specific failure mode gets a severity score of 8 or even 9 out of 10.
It is classified as a high AP, a high priority risk.
Which means the accounting department opens the checkbook.
They are willing to spend significant money, weight, and engineering resources to prevent it.
Precisely. And the physical upgrades detailed in the design phase are fascinating. The first major shift is abandoning standard round wires altogether.
No more regular wires.
No, instead of a messy bundle of loose, floppy copper wires that can get tangled or pinched, the design mandates the use of SPC.
Flexible printed circuit.
Yes.
For those picturing it, these are those flat orange ribbon-like cables you sometimes see if you open up a smartphone or a laptop, but scaled up massively for high-voltage automotive use.
Polyimide flexible printed circuits offer massive structural advantages. They are two-dimensional. The copper traces are etched directly into the flexible plastic film.
So you don't have individual wires rubbing against each other.
They lie perfectly flat, drastically reducing their vertical profile and making them much harder to crush.
But the engineers go further. The junction where the tiny, rigid ceramic NTC thermistor is soldered onto that flexible plastic circuit is a major mechanical weak point.
It is. As the flexible circuit bends and vibrates, it creates immense shear stress on the tiny, rigid, microscopic solder joints.
That's where the vibration would slowly snap the connection.
Wow.
How do they reinforce it?
They mandate the use of underfill glue.
Underfill glue.
After the sensor is soldered to the flexible circuit, automated machines inject a specialized, low-viscosity epoxy resin completely underneath and around the tiny component.
It fills all the gaps.
This underfill cures into a rigid block, literally cementing the sensor to the board. It acts as a microscopic shock absorber, distributing the mechanical vibration and CTE thermal stress across the entire plastic film, rather than concentrating it on the fragile solder joints.
The spec dictates that all these components must meet the AEC Q200 standard, right?
Yes, an automotive-grade benchmark that requires surviving hellish mechanical and thermal conditions.
So it is microscopic armor.
Yeah.
But what about the terrifying detachment issue we discussed earlier? The P0A9C drift failure, where the glue holding the sensor to the battery cell fails and the sensor pops off to measure the ambient breeze.
The glue failure.
Right, they can't just use stronger glue, can they?
Right.
Chemical adhesives will always degrade eventually over a 10-year lifespan.
That is exactly the conclusion the engineers reach in the DFMEA. Relying solely on chemistry is a single point of failure.
So what do?
They introduce mechanical redundancy. The spec dictates the mandatory integration of physical stainless steel spring clips.
I love this concept. It is so brutally simple compared to the complex software algorithms. It is literally just a piece of bent metal.
But perfectly engineered bent metal. You design a custom high-tension stainless steel spring clip that permanently clamps down over the top of the sensor probe.
It just holds it there.
It uses constant mechanical spring force to physically press the sensor flat against the aluminum shell of the battery cell or the copper bus bar under high continuous pressure. It is literally putting a heavy-duty seatbelt on the sensor.
Exactly. Even if the thermal adhesive completely dries out, cracks, and turns to dust 10 years from now.
That spring clip is physically pinning the sensor to the hot surface, ensuring it maintains a perfect thermal pathway and can never peel off and read the air again.
Mechanical redundancy guarantees long-term thermal integrity. And to solve the issue of the flexible circuits getting crushed by the heavy power bus bars, the mechanical design rules mandate the creation of dedicated routing channels.
They hide the wires.
They don't just lay the flexible circuits on top of the modules anymore. They build literal plastic trenches into the injection-molded battery framework, specifically for these signal lines to sit in safely below the surface.
They create a hard, physical architecture that isolates the delicate sensor lines from the dangerous heavy power lines.
They engineer the 3D environment so that a physical short-circuit path simply does not exist. So they flat-pack the wires into flexible ribbons, they armor the joints with underfill, they seatbelt the sensors with steel clips, and they hide the ribbons in plastic trenches.
The physical design is incredibly robust.
But here's a question that always fascinated me about battery design. How do they know where to put them?
The sensors.
Yeah. You have an 80 kilowatt-hour pack made of hundreds, maybe thousands, of individual cylindrical or prismatic cells. You cannot physically afford, in cost or computational power, to put a dedicated temperature sensor on every single millimeter of every single cell.
No, you definitely can't.
So how do you choose which cells get a sensor?
That is where simulated perfection drives the design. The engineers do not just guess where to stick these thermistors, and they don't just spread them out evenly like polka dots.
No.
They rely heavily on advanced CFD, computational fluid dynamics, and multiphysics thermal flow simulations. Before a single physical prototype is built, they construct a perfect, mathematically rigorous digital twin of the entire battery pack on a supercomputer.
A digital twin, and then they torture it.
Relentlessly. They run the digital model through simulated extreme operating conditions. Massive, sustained acceleration up a mountain pass, rapid DC fast charging in a simulated desert environment, track day power cycling.
Just beating the virtual pack up.
Exactly. They map the complex internal thermodynamics. They are looking for the absolute extremes of the pack. They simulate the exact locations of the hottest points, the core Joule heating zones.
Joule heating, that's the heat generated purely by electrical resistance when you push massive current through a conductor, right? I squared R losses.
Correct. They map where the current density is highest and where that Joule heating builds up the fastest. But equally important, the CFD software maps the fluid dynamics of the liquid cooling system.
Finding the cold spots, too.
It finds the coldest points and, crucially, the dead zones in the cooling channels. The microscopic areas where the glycol coolant fluid doesn't circulate well due to turbulence or flow restrictions.
So they find the spots that naturally get the hottest and the spots that receive the worst cooling.
The ultimate worst-case locations.
They mathematically prove where the thermal bottlenecks are.
And then they position the physical NTC thermistors precisely at these proven extreme locations.
Ah, the logic is simple but impenetrable. If you actively monitor the worst possible, hottest theoretical spots in the pack and ensure those spots stay below the safety threshold, you mathematically guarantee that the rest of the pack is safe.
You eliminate thermal blind spots by designing a targeted surveillance network based on fluid dynamics.
It is brilliant. Find the worst-case scenario mathematically and monitor it physically. But as we transition into the fourth major dimension of our outline, we hit a very hard, very expensive truth in the automotive industry.
What's that?
A perfect design on a computer screen, a beautiful multi-physics simulation, and a perfectly engineered steel clip mean absolutely nothing if the product is built poorly on the factory floor by a tired worker at the end of a long shift.
Yes. A perfect blueprint doesn't survive a sloppy factory.
This brings us to manufacturing paranoia, or the PFMEA phase process failure mode and effects analysis. How do factories guarantee perfect assembly of these delicate systems at a scale of millions of units a year?
The primary directive of the factory floor is the complete and utter elimination of human variance. They implement strict poka-yoke, which is the Japanese concept of mistake-proofing protocols.
Okay, mistake-proofing.
Every single step must be repeatable, verifiable, and immune to human error. And in this engineering spec, the obsession with process control starts with something that sounds incredibly mundane: the glue.
Yes, I noticed this. The spec explicitly lists the thermal glue dispensing process as a KCC, a key control characteristic. Now, I have to push back here for the sake of anyone who has ever built a model airplane.
All right, go ahead.
It's just glue. It's the sticky stuff that holds the sensor on before the spring clip clamps over it. Why is the exact volume, the specific chemical mixing ratio, and the robotic precision of the glue dispensing tracked so neurotically on the factory floor?
Why is glue a key control characteristic for a high-voltage safety system? Yes.
Exactly.
Because in the realm of thermodynamics, this glue isn't just sticky stuff. It is the physical bridge that transfers thermal energy from the hot battery cell into the sensor.
It's a thermal bridge.
The spec mandates a highly specialized two-part thermal structural adhesive. It is infused with thermally conductive particles, often aluminum oxide or boron nitride.
To help the heat flow.
If the automated dispensing machine gets the mix ratio even slightly wrong, the thermal conductivity plummets. But the bigger danger is physical application.
How so?
If the dispensing nozzle speed fluctuates, or if the pressure drops for a microsecond, the machine might trap microscopic air bubbles voids inside the glue bead as it applies it to the sensor.
And we established earlier that air is a terrible conductor of heat. It is a thermal insulator.
Exactly. Those microscopic air bubbles act as tiny thermal insulators sitting directly between the hot battery cell and the NTC thermistor.
Oh, wow.
The heat has to physically fight its way around those bubbles to reach the ceramic chip. This creates a severe thermal lag.
I see the cascading failure now. The cell itself might spike in temperature incredibly rapidly during a short circuit, but the sensor, sitting just a millimeter away but hiding behind a microscopic wall of air bubbles in the glue, doesn't actually feel that heat rise for several seconds.
And in battery safety, a thermal delay of several seconds is an eternity.
It's too late.
It renders all that brilliant microsecond software logic we discussed completely useless. The BMS software can only react to the data the sensor provides.
If the factory process introduces a physical thermal lag via air bubbles, the computer's reaction time is artificially delayed.
The cell goes into thermal runaway while the computer is waiting for the heat to penetrate the bubbles.
That is horrifying.
That is exactly why the glue dispensing is elevated to a key control characteristic. The volume, ratio, and void-free application are monitored continuously by statistical process control vision systems.
Just to ensure absolute perfection in every single drop before the spring clip is ever applied. The microscopic integrity of a single drop of glue dictates the safety of a $60,000 vehicle.
Huh?
That level of manufacturing paranoia is staggering.
It's necessary.
What else are they doing on the floor to eliminate variance? The documentation talks heavily about robots and armor.
Yes. For the actual physical assembly, stacking the heavy battery modules, routing the flexible printed circuits into their plastic trenches, and torquing down the heavy metal lid, the spec mandates the use of 100% multi-axis industrial robots.
Why mandate robots?
Because human hands, while dexterous, are inconsistent. A human worker trying to route a wiring harness for 8 hours a day on an assembly line will inevitably pull a wire slightly too hard, bend a flexible circuit at too sharp of a radius, or accidentally pinch a wire under a bolt.
The human element is the enemy of consistency.
Yeah.
Robots don't get tired, they don't lose focus.
Exactly. Robots move with absolute, repeatable, sub-millimeter precision. Furthermore, the assembly stations utilize dedicated jigs and physical limiters.
What do those do?
So even if a robot arm experiences a software glitch and pushes down too hard while installing the cover plate, a solid steel physical block stops the outer shell from crushing down on the wire channels.
It is accident-proof assembly at an industrial scale.
It has to be.
Okay, so the robots ensure the wires aren't crushed, solving the P0A9D short circuit problem at the force. But what about the armor? We talked at length about moisture and condensation causing those insidious P0A9C drift errors where water creates a parasitic parallel leak and gaslights the computer.
Right, the lying sensors.
How does the factory stop moisture when a battery pack isn't perfectly hermetically sealed?
They apply an incredibly robust physical armor directly to the printed circuit boards holding the sensors. It is a process called conformal coating.
Conformal coating, what is that?
After the surface mount technology, or SMT, process successfully solders all the tiny resistors, ADC chips, and thermistors onto the board, the entire board is sent through an automated spray chamber.
Like a car wash, but for electronics.
Basically, the board is coated in a high-density, often vacuum-sealed layer of specialized polymer conformal coating, typically a silicone, acrylic, or urethane blend. It is basically an advanced, impenetrable, electrically insulating varnish.
It is essentially shrink-wrapping the bare electronics in a waterproof shell.
Precisely. The automated optical inspection system specifically verify 100% conformal coverage over the exposed NTC connector pins and the delicate pull-up resistor circuits.
So water can't get in at all.
By totally encapsulating those sensitive areas in a hydrophobic polymer, they physically block out any moisture, dew point condensation, or high humidity from ever touching the bare metal traces.
The water simply beads off the plastic shell, completely eliminating the root cause of the parasitic parallel leak.
The physical cause of the lie is eradicated.
Okay, so the robots assemble it perfectly without crushing wires, the glue is flawless and void-free, and the circuit boards are varnished against moisture. The battery pack is fully built.
But before that massive, heavy box is allowed to leave the factory, get loaded onto a truck, and bolted into a car, it faces one final interrogation on the factory floor.
The end of line, or EOL, testing.
Yes. EOL testing is the final gatekeeper. The factory does not assume the build was perfect. They force the pack to prove it.
How?
Before the battery pack ships, it is plugged into a massive automated test system. First, they execute a comprehensive static check. While the battery is just sitting there in the factory at a stable room temperature, the test system reads the precise electrical resistance of every single NTC thermistor in the pack simultaneously.
Checking their pulse, basically.
It checks for absolute consistency. If one sensor out of 100 is reading a slightly different baseline resistance than all the others, if it shows even a hint of an inherent manufacturing drift or a weak solder joint, that entire battery pack is rejected and sent to a rework station.
They aggressively kick out the latent defects before the pack ever sees a road.
It's a high-tech roll call to make sure everyone is healthy.
But they don't just test it while it's sitting quietly at room temperature. The engineering document details a procedure called the Dynamic Heavy Load Pulse Discharge Test.
That is the dynamic test.
Now that sounds aggressive. They're actively attacking the battery on the assembly line.
They are. They fundamentally do not trust a static sensor reading. The only way to prove a thermal sensor works is to subject it to dynamic heat.
How do they generate the heat safely?
The automated EOL test system hits the fully assembled battery pack with a massive sudden pulse of electrical power. They demand a huge, instantaneous current discharge, simulating a driver stomping the accelerator pedal to the floor.
Which instantly generates a massive wave of real, significant joule heating inside the chemical cells.
Exactly. As the cells rapidly heat up from the current pulse, the automated test system watches the digital temperature readings of every single NTC sensor in real time.
It meticulously monitors the mathematical slope of the temperature rise.
Yes.
It's checking the reaction time and wants to see if that heat transfers quickly across the glue.
It is the ultimate validation of the KCC glue process. It is proving that the thermal adhesive is perfect and that there is zero physical thermal lag.
If a specific sensor's temperature reading lags behind the actual power pulse by even a fraction of a second compared to its neighbors, the test system knows the physical thermal pathway is compromised.
Perhaps there was a microscopic air bubble in the glue, or the spring clip isn't clamping hard enough. The pack is instantly failed.
It is 100% factory verification of dynamic thermal response.
Yeah, exactly.
That is awe-inspiring. The physical design is bulletproofed with flexible circuits and steel clips. The manufacturing is paranoid, utilizing robots, vacuum armor, and void-free glue. And the individual assembled packs are interrogated with massive power pulses to prove they react instantly.
It's a very thorough process.
We should be good to go, right?
Mm-hmm.
The engineers can go home, and the factory can start pumping out thousands of these cars a day.
Not yet. We have one final brutal step.
This brings us to Section 5, the torture chamber.
The DVP&R phase.
Design verification plan and report. This isn't about testing every single pack on the line. This is about taking the finished, mass production intended blueprint and trying your absolute hardest to physically and electronically destroy it.
Just to mathematically prove the design is robust enough for the real world?
The DVP&R is the ultimate, uncompromising validation loop. The engineers have to empirically prove that everything we just discussed over the last hour, the hard voltage limits, the complex Steinhardt math, the temporal software algorithms, the physical conformal armor, actually works in concert under absolute worst-case scenarios.
And the validation starts in the digital realm with the speed test.
The hardware in the loop, or HA, F2TI test.
FTTI, fault-tolerant time interval.
This is all about the stopwatch. How exactly does this digital torture test work?
They take the actual production battery management system hardware, running the final mass production software code, and hook it up to a massive, incredibly complex computer simulator.
Like a massive video game for the computer.
This simulator tricks the BMS into thinking it is driving a real car down a virtual highway at 70 miles per hour, pulling real power and monitoring fake cells.
And then the test engineers maliciously attack it.
They become the chaos of the real world.
Precisely. Through the simulator, they artificially inject critical hardware faults.
They literally had a software switch to instantly sever the virtual wiring of an NTC sensor, simulating an instant 5-volt open circuit.
Or they shorted straight to ground, simulating an instant 0-volt short circuit while the virtual vehicle is at full highway speed.
Boom! A catastrophic, instantaneous hardware failure while driving.
What is the software required to do, and how fast?
The system is judged by incredibly strict, uncompromising time limits. The moment the virtual fault is injected, the stopwatch starts.
Tick-tock.
The BMS software has exactly 500 milliseconds, half of 1 single second, to recognize the voltage drop, filter out any potential electromagnetic interference or transient electrical noise, confirm the fault is genuine, and officially declare the P0A9D or P0A9E error code internally.
This 500 millisecond period is known as the debounce window. Half a second to realize you have been blinded.
Right.
Why 500 milliseconds? Why not react in 1 millisecond if the computer is so fast?
That is the fundamental paradox of fail-safe engineering. If you react in 1 millisecond, your system is too sensitive.
How so?
A random burst of electromagnetic interference from a passing power line might cause a tiny microsecond dip in voltage. If the system reacts to that, you get false positives, and the car shuts down on the highway for no reason.
Ah, so it has to wait just a beat to make sure it's a real failure.
Exactly. 500 milliseconds is the mathematically calculated sweet spot. It is long enough to filter out random electrical noise, but short enough to catch a real break before a cell can physically heat up to a dangerous level.
Okay, so they have 500 milliseconds to confirm the fault, And then what?
The clock keeps ticking. From the exact moment the fault was initially injected, the system has exactly 2.0 seconds total to execute the entire sweeping failsafe protocol we discussed earlier.
2.0 seconds.
In those 2.0 seconds, it must recognize the fault, execute the maximum temperature substitution strategy to digitally grab the neighbor's temperature data, communicate the critical torque reduction request over the CAN bus to the vehicle control unit, and physically command the heavy liquid coolant water pumps and front radiator fans to spool up to 100% maximum speed.
2.0 seconds from a broken wire to screaming radiator fans and throttled power.
Yes. There is absolutely no hesitation allowed in the logic. The engineers monitor the CAN bus response times. If the system takes 2.1 seconds to command the fans, the entire software architecture fails the DVPNR, and the car cannot legally be sold. It must be rewritten and revalidated.
That is the digital speed test. It proves the brain works. But then they move on to the physical torture of the nervous system.
The AEC Q200 torture test.
I was reading this specific section of the engineering document, and it honestly sounds absurd. What they do to these physical components is practically medieval.
It is designed to simulate a lifetime of extreme compounding abuse in a highly compressed time frame.
They just beat it up.
They take the fully assembled NTC thermistor, perfectly underfilled and welded to its flexible printed circuit, and they bolt it to a massive industrial 3D random vibration table.
This isn't just shaking it up and down.
No, this machine violently vibrates the component across all three X, Y, and Z axes simultaneously, utilizing complex harmonic frequencies designed to mimic the worst possible washboard dirt road imaginable.
But they don't just shake it. That would be too easy.
Right. While it is being violently vibrated, they slide the entire shaking apparatus inside an environmental test chamber.
And they subject it to extreme thermal shock.
They aggressively cycle the ambient temperature from negative 40 degrees Celsius, a deep, brittle freeze, all the way up to positive 85 degrees Celsius, which is a baking desert heat.
And it is the speed of that temperature transition that is so incredibly destructive, right?
Exactly. The chamber doesn't warm up slowly. It forces the temperature to change at a brutal, sustained rate of 10 degrees Celsius every single minute.
Why is that specific rate so damaging?
Because it maximizes the CTE mismatch shear forces we discussed in the first section.
The epoxy and the ceramic fighting each other.
By changing the temperature that rapidly, you force the epoxy shell and the ceramic chip to expand and contract violently and unevenly while they are simultaneously being shaken apart by the vibration table.
You are attacking the chemical bonds of the glue, the molecular structure of the epoxy, and the crystalline lattice of the solder joints all at the exact same time.
It is relentless.
And how long do they run this chamber of horrors? A few hours. A day.
They run this test continuously, without stopping, for 300 hours.
300 hours. That is nearly 2 weeks of non-stop deep freeze, baking heat, and violent 3D shaking. How can any physical object survive that? What does the component have to do to actually pass this test?
The pass criteria are incredibly stringent. After 300 hours of continuous torture, the engineers remove the component and measure the electrical resistance of the circuit.
Checking its pulse again.
The dynamic resistance cannot have fluctuated by more than a microscopic 0.05 ohms from its original baseline measurement. It must remain electrically perfect, proving the internal wires haven't stretched or degraded.
Surviving that electrically is impressive enough.
But electrical survival is not enough for validation. They then physically dissect the component.
They cut it open?
They cut the sensor in half, polish the cross-section to a mirror finish, and place it under a high-power scanning electron microscope, NSEM.
They are looking at it on a cellular level.
They meticulously inspect the epoxy encapsulation, the microscopic solder joints, and the ceramic crystal itself. They must find absolutely zero stress cracks, zero solder fatigue voiding, and zero microfractures in the ceramic.
If the electron microscope finds a single microscopic crack after 300 hours of torture, the physical design is rejected and sent back to the drawing board.
It is the definition of rigorous engineering.
But my favorite test in this entire document, or perhaps the most horrific one, is the electrochemical migration test, or ECM test.
Yes, the ECM test.
I noted this when reading the source material because it sounds like something straight out of a sci-fi horror movie. They're basically trying to grow metallic monsters on the circuit board.
It is a profound chemical torture test.
What are they trying to prove?
The engineers are trying to verify that the conformal coating armor we talked about earlier is truly impenetrable under the worst possible real-world conditions.
Right, because in a real vehicle, it is entirely possible that the battery's internal liquid cooling system might spring a microscopic leak over years of use, slowly dripping highly conductive ethylene glycol antifreeze directly onto the circuit boards.
So in the lab, they don't wait for a leak.
They just attack it directly.
They intentionally drip aggressive coolant fluid and salt electrolytes directly onto the bare pins of the thermistor connector. They actively poison the board.
And then they bake it.
They place the poisoned coated circuit board into what is called a dual 85 chamber. That means maintaining an environment of 85 degrees Celsius and 85% relative humidity.
But this spec goes further.
Right. Or in the case of the specific ultra-strict engineering source material, an even more punishing 95% relative humidity.
It is a scorching, boiling, humid jungle environment.
And while the board is sitting in this toxic, humid oven, they apply a constant 5 volts of electrical direct current bias to the pins.
And they leave it in that toxic oven for 500 hours, over 3 weeks. What exactly are they looking for? What is the physical danger here?
They are looking for the growth of dendrites.
Dendrites, what are those?
When you combine electrical current, moisture, chemical electrolyte contaminants, and high heat, you trigger a destructive electroplating process called electrochemical migration.
Okay.
The metal ions from the solder joints, usually tin or silver, will undergo anodic dissolution. They literally dissolve into the moisture and begin to grow across the surface of the circuit board toward the neighboring oppositely charged pin via cathodic deposition.
That's wild.
They form tiny, highly conductive metallic crystals that look exactly like jagged tree branches or metallic ivy creeping across a brick wall. These are dendrites.
So the metal itself becomes alive, reaches out, and tries to short-circuit the board. It is literally trying to build its own bridge to cause a P0A9D failure.
Exactly. If a metallic dendrite grows far enough to physically touch the adjacent pin, you have a hard short circuit, and the sensor fails catastrophically.
So the entire goal of the 500-hour ECM test is to mathematically ensure that the conformal coating armor blocks the moisture and the electrolytes so perfectly that these metallic monsters simply cannot grow.
Throughout the 3-week test, the automated equipment constantly measures the leakage current flowing between the pins. To pass, the leakage must stay under an incredibly tiny threshold of 1.0 milliamp.
Wow, just 1 milliamp.
And the overall insulation resistance of the coating must remain over 100 megaohms. If the engineers pull the board out after 500 hours and the electron microscope finds even a microscopic trace of dendrite growth starting on the surface, the conformal coating formulation or application process fails validation.
It is absolutely phenomenal. They shake it on 3 axes, they freeze it, they bake it, they purposefully poison it with electrolytes, and they try to grow metal ivy on it.
And it has to survive all of it.
And finally, the source material details the last checks, the statistical proof that mass production can maintain this insane standard across millions of units. They demand a SIPIPIC process capability index of greater than or equal to 1.67 for the resistance distribution.
Yes. SPIPIC is a statistical measure used in Six Sigma manufacturing to determine how tight the manufacturing tolerances are compared to the allowable limits.
The 1.67 is good.
A SPIPIC score of 1.67 is incredibly high. It is approaching Six Sigma perfection. It mathematically proves that the manufacturing process is so tightly controlled and the robots are so accurate that out of millions of sensors produced, the variance in their natural baseline resistance is practically zero.
They are not just similar, they are statistically identical clones of precision.
Yes.
And the very last physical check they dictate, the non-destructive pull test. They take the finished wiring harness, clamp down on the delicate NPC plastic connector, and they literally try to rip the wire out of the housing using a specialized machine pulling with 80 newtons of force.
80 newtons translates to a significant amount of weight, roughly equal to hanging 18 pounds of dead weight directly off that tiny, fragile little wire.
And it has to hold.
Every single connector design must withstand that violent shear force without the metal pins wiggling loose or the plastic snapping. It proves definitively to the engineering team that the physical connection is robust enough to survive years of pothole impacts, suspension bottom-outs, and harmonic road vibrations.
Without ever suffering from that pin pull-out failure we discussed in the open circuit section.
And crucially, the results of that pull test for every single harness installed in a car are digitally recorded and permanently bound to the factory's manufacturing execution system.
Oh, the traceability.
If a car fails in the field 10 years later, they can track the exact serial number back to the exact machine that pulled it on a Tuesday in 2026.
The traceability is total.
Yeah.
Unbelievable. What an incredible journey.
We covered a lot of ground today.
We really did. We have taken a massive, exhaustive, deep dive today into a world most drivers will never see. We started by looking at a tiny ceramic bead, the NTC thermistor, and explored the violent mechanical crushing and the internal microscopic CTE warfare that causes it to fail.
We looked at how the car's brilliant digital detective uses hard voltage asymptotes, thermodynamic mass logic, and spatial geometry to instantly spot those failures, catching the liars and taking aggressive, pessimistic action to substitute temperatures and throttle power just to keep you safe.
And we saw how the engineering teams actively fight back against the laws of physics. They design flexible, two-dimensional armor, they use supercomputers and CFD to mathematically map the thermal hot zones, and they implement deeply paranoid manufacturing controls.
Sweating over the microscopic air bubbles in a single drop of glue and sealing the boards in vacuum-sprayed polymer armor.
And finally, we walked through the ultimate gauntlet. 300 hours of freezing, shaking torture, and 500 hours of poisonous electrochemical dendrite growth just to mathematically prove the design is worthy of being bolted under the floorboards of your car.
It is a towering monument to the paranoia of safety engineering.
It really is. But as we wrap up this deep dive, I want to leave you with a provocative thought, something inspired by the very last, almost throwaway note in our engineering source material.
Yes. The source material ends with a fascinating, almost philosophical question posed to the future engineering team.
We have spent this entire time talking about how engineers design all these hard limits, the 0.2-volt floor, the 500 millisecond debounce threshold, the spatial matrix. They establish static, mathematical lines in the sand.
But the text ends by asking if the engineering team needs to start utilizing Python to create dynamic, visual simulations of these nonlinear temperature curves.
Think about the implication of that for a second. We're reaching a point where static engineering math, as incredibly complex as it is, simply isn't enough anymore.
The sheer complexity of modern ultra-high-density cell chemistry and the massive power demands of fast charging are outgrowing the traditional diagnostic tools. A 500 millisecond reaction time is fast, but it is still inherently reactive.
Exactly. The ultimate insight here isn't just about a broken wire, it's the philosophical engineering problem of trust and time. As high-voltage batteries become increasingly energy-dense and vehicles push more and more power, will our software algorithms need to fundamentally evolve?
Will we need programmatic, dynamic simulations running in real time on the vehicle's computer?
Could we soon see essentially predictive AI integrated directly inside the battery management system? An AI that analyzes the subtle, microscopic, sub-millivolt fluctuations in resistance to guess a mechanical sensor failure or predict a thermal drift before the hardware voltage ever actually drops to that 0.2-volt limit.
Will the car of tomorrow know its sensor is going to break on a Tuesday, days before it actually happens?
It is a profound, paradigm-shifting direction for the automotive industry, moving from reactive diagnostics, catching the failure after the wire snaps and dealing with it in half a second, to truly predictive AI-driven safety.
It is the transition from a nervous system that feels pain to a brain that predicts injury.
It changes everything about how we view automotive reliability. Thank you so much for joining us on this exhaustive deep dive into the microscopic, hyper-paranoid world of battery safety engineering. The next time you are cruising down the highway at 70 miles per hour, totally relaxed, listening to the hum of the tires, take a brief moment to look at the electric cars driving around you, or perhaps the one you are driving yourself.
Have a newfound appreciation for those tiny ceramic beads.
The rigid steel spring clips, the flawless drops of underfill glue, and the hypervigilant digital detective constantly working in the background beneath the surface. They are the unsung, microscopic heroes constantly fighting a war against physics, ensuring your vehicle never ever loses its sense of touch.